Today we are going to look at the periodic table a little bit more, now focusing in on the attraction between the nucleus, which has protons in it, so it's positive, and the negatively charged electrons in its energy levels. This is defined as Coulombic attraction. So if you think about magnets, Coulombic attraction also applies to their force of attraction between one another. When the opposite poles are close together, they attract more than if they're farther apart. And if you have a stronger magnet, then it's going to pull with a stronger force than if it was a weak magnet. The same applies for our nucleus. If the nucleus and the electrons are close together, then it will have a stronger force of attraction than if they're farther apart by multiple energy levels. And if that nucleus is stronger because it has more protons in it within the same energy level, the same distance, but more protons, then we'll see a stronger pull from that nucleus. So let's catch up our notes here on Coulombic attraction. This is our attraction between oppositely charged. So we've got protons and electrons. Those oppositely charged particles in the atom. Remember, protons are in the nucleus, and our electrons are in the energy levels. The two factors that affect the force of attraction is the number of protons that are in the nucleus, that will cause a stronger force, and the distance apart between the nucleus and the electrons. The farther apart, the weaker the force. We call these two attributes of distance and number of protons nuclear charge and shielding. So nuclear charge is referring to the number of protons that are being added in the same energy level. If you remember from last week, atoms that are in the same row or period, that will be from left to right, they are in the same energy level. But atomic number continues to increase as you go from left to right. So within that same energy level, we are gaining more protons. So as a result, as protons are added, the nucleus becomes stronger going from left to right. More protons equals stronger nucleus. And as a result, our atom will be pulled more tightly in. So it'll get smaller, and the electrons will be pulled much more tightly towards the nucleus. Shielding is looking at the trend that goes up and down between our atoms. And remember, as we go down, we're getting more energy levels. The first period has 1 energy level compared to the 7th period has 7 energy levels. If you look at the picture in the example, this is going from the 2nd energy level to the 3rd energy level, and you can notice there's a difference in the size of the atom, lower down is bigger, and in the force of attraction. The more bolded arrow is stronger pull because it's closer to the nucleus, and our kind of weaker pull is down at the bottom because it is farther from the nucleus. So the trend vertically is as the distance increases, our force of attraction will decrease. More distance from energy levels equals weaker pull. We've already started talking about the application without even knowing it, because as it pulls stronger, it's going to make the atom smaller, and as it pulls weaker, it's going to make the atom larger. And of course, if the distance is increasing from the nucleus to the electron, the atom is getting bigger. So let's take a look at our first trend, atomic radius. An atomic radius, simply put, is the size of an atom. A more technical definition is the distance between the nucleus of an atom and its valence electrons, but both describe the size of the atom. So if we have a large radius, we've got a big atom. If we have a small radius, we have a small atom. So our first trend, let's look at the vertical, which is in example 1 pictures. We just talked about this as we go down the periodic table, we're adding energy levels. This picture goes from the second to the third energy level, and you'll notice which of these 2 atoms is larger, the one that has more energy levels. And this would be true for all of our atoms. Ruh-roh. Okay, there we go. As we move down, our shielding is going to cause our atom to get larger. The atomic radius will increase. That means our largest atom on the periodic table vertically would be in the 7th period. So in the first group, that would be francium. Now that asks or leads us to ask the next question, what if we go from left to right? Well, basic logic would tell us as we have a higher atomic number, it's getting more stuff in it, so it should be getting bigger, right? However, protons are charged, so we actually see the opposite happening because our more protons cause a stronger magnet, not necessarily a larger atom, which pulls in the electrons tighter. If you look at example 2, you'll see a picture of this to help you visualize. Within the same energy level, let's say on the left here we have 1 proton in the nucleus, then on the right we have 2 protons. The arrow showing the force of attraction is stronger, making our atom slightly smaller because of that stronger attraction toward the nucleus. So as we move from left to right in the same energy level, our atomic radius or size decreases. Let's apply the atomic radius trend here in our examples, starting with that vertical shielding trend. And you'll need a periodic table handy for this. If you don't have one, go ahead and pause the video and grab a periodic table. The atomic radius trend we just summarized increases going down and decreases going across. The shielding property, this is going to be looking at the vertical trend. So our question says, which element has a larger atomic radius? Find calcium and barium. You'll notice that they're in the same column, the same group. So we're just looking at that vertical trend. And as we go lower, we're going to get bigger because of more energy levels. So our correct answer for this is barium. Which element has a smaller atomic radius? By the opposite reasoning, higher up on the group or column is going to be smaller, that's hydrogen. Now let's look at the vertical, nope, we just did vertical. Let's look at the horizontal trend. Going across, we're going to decrease in size because within that same energy level, we have a stronger pull in our magnet, if you will, of the nucleus. Which element has a larger atomic radius, sodium or sulfur? Find them. Sodium has less protons in its nucleus within that energy level, so it would be the largest. Which element has a smaller atomic radius, carbon or nitrogen? Nitrogen. So there's atomic radius based on the pull of the electrons, both horizontally and vertically. The next two properties we're going to discuss, electronegativity and ionization energy, are very similar, but kind of worded oppositely of one another. So the electronegativity of an atom refers to its pulling power on the electrons. If we have a stronger force of attraction, then we're going to be having a higher electronegativity. That means when our atom is smaller, our force of attraction is going to be larger. So our properties are going to have opposite trends here. When it's smaller, we have a bolder arrow in our pictures because it's closer. The smaller the distance, the greater the attraction. So going down, shielding, we get farther away from the nucleus, causing a weaker pull. So down, it decreases. Going across, our magnet nucleus is getting stronger, so our pulling power increases going across. Now, if you think about the properties of kind of metals and nonmetals, this also makes sense because nonmetals want to gain electrons. Think about the halogens. They have 7, so they're going to pull on their electrons really hard, and even the electrons of other atoms in order to reach 8. However, the noble gases have no cares in the world if they can pull electrons or not. They are going to actually have a zero electronegativity because they don't really care about grabbing electrons from other atoms. While I'm here, this pulling power is talking about the electrons on neighboring atoms. Because you might be thinking, well, the noble gases want to keep their electrons, and you're correct. But they don't really care about pulling electrons from other atoms. They are already stable. But halogens, they say, sign me up. I need one more. Metals, though, they'd rather lose their electrons than gain them. So they're going to hold on to their electrons more tightly, more loosely, readily giving them up. That's why they have a low energy of pulling power. Let's do our examples. So which element vertically attracts electrons to itself more effectively? So we're looking for higher electronegativity, potassium or francium. Potassium. It's smaller, that force is going to be tighter, higher up. Which element has lower electronegativity? Now we're going to look farther down the periodic table. Aluminum or boron? The aluminum. Now the horizontal pattern. Which element attracts electrons to itself more effectively? This would be a higher electronegativity, either beryllium or oxygen. Further to the right has a stronger electronegativity. And which element has a lower electronegativity? Fluorine or neon? Well, lower electronegativity generally would be to the left. It's fluorine. But remember, neon is a noble gas. It doesn't even have an electronegativity value because it doesn't care about pulling electrons. So neon would be the lower electronegativity. Kind of a trick there. Okay, our last trend is ionization energy. And we define ionization energy as the energy required let me try that again. The energy required to remove an electron. This is kind of the same trend as electronegativity, just worded in the reverse. The stronger something's pulling power is, the more energy is going to be required to remove it. And the less pulling power, the easier it will be to kind of take one away. So we will find that our vertical trend, if you're thinking about plucking off the electron, you'll want the one that has a weaker pull, which has a larger distance. So it will be decreasing going down, easier to pull off. And horizontally going across, it's going to get stronger, so it's harder to remove, requiring more energy. This time the noble gases are included in the trend because you think about their electrons, they're very stable with 8, they're happy with 8, they do not want to have an electron stolen from them, so they have a very, very high ionization energy. So here are our 3 trends. Let's now finish up with the examples for ionization energy, and then we will be finished. Which element more easily loses electrons? That's a low ionization energy. So we're going to be looking for more distance farther down the periodic table. That would be arsenic, which requires more energy to release an electron. This should be higher up on the periodic table because it's got a stronger pull when it's closer. And lastly, which element more easily loses electrons horizontally, strontium or iodine? That would be strontium. Weaker magnetic nucleus makes it easier to remove. And which element requires more energy to remove an electron or higher ionization energy? Cesium or astatine. Stronger nucleus, astatine would be a higher ionization energy.